So last thing we're going to look at is the second half of 6.1, and then we'll look at a little bit of 6.2. So we've talked about how to convert between radians and degrees. That's going to be important, because the first thing we're going to do is we're going to look at a formula to find what's called arc length. Now this formula we're going to look at, it's going to depend on having your angle in radians. So if they give you something in degrees, the first step is going to be to change to radians. So first thing I need to tell you about arc size is how it connects to angle size. And they are what we call directly proportional. I'm going to draw a picture of what that means. It's a very easy concept to understand. But arc size and angle size are directly proportional. Okay, so let me make a circle. Eric, how big is that angle that I just made?
90.
90. And there's the arc for a 90-degree angle in that circle. Okay, now I'm going to go like this. Jacob, how big is the angle I just made there? 180. How does the angle that I had in the first picture compare to the angle I had in the second picture? Yeah?
Double.
It's double. How does the arc I had in the first picture compare to the arc I have in the second picture?
It's also double.
It's double. That's what directly proportional means. If you double the size of this angle, then you double the size of this arc. If you made this angle half as big, you would make the arc half as big. So however you change the angle, the arc changes exactly the same way. And that's called directly proportional. So, if two things are directly proportional, then what you can do is set up a proportion to solve a question about them. If they weren't directly proportional, you couldn't set up a proportion. But they are, so we will. So, we're going to start with this diagram. What I've drawn in that diagram are two angles and two arcs. Angle theta and arc S. Angle theta 1 and arc S1. R is just the radius. All those black lines from the center are R. Okay, but I'm not going to label them all R. Now, what we need is some kind of fact between angle size and arc size. And I'm going to go back to something I talked about yesterday to kind of show you how this is going to work with something you're probably already familiar with. I want to convert feet to inches. Can somebody give me a true fact about feet and inches? No half inches. Feet and inches. What's the fact we can use there? Yeah.
It's 12 inches in a foot.
There's 12 inches in 1 foot. Now, if somebody said, okay, how about in 8 feet? How many inches? Well, that's easy. Just put 8 feet right here. Put X inches right there. Cross multiply and I can solve. But the whole key to setting this proportion up was that fact that I had on the left. Now, how did you know that fact? Yeah.
Do we use feet and inches every day?
All right, so yeah, you use it a lot. It's a unit you're familiar with. You probably learned that back in like elementary school, right? 12 inches in 1 foot. It's just a fact we know that's true, right? We've got to have a fact that we know that's true to do this as well. So, any fact, doesn't matter. The fact that you have a 12 here and a 1 here doesn't mean you have to put an 8 here. I could put a 9 there. I could put a 10. I could put a 4.3. I could put anything I want here. I just had 2 specific numbers here that were true. That's all I need. Any 2. 24 and 2 would also work. You just need something that's true. So, we just need something that's true here. So, yesterday, first thing I did is I defined what a radian was visually. And does anyone remember what I said? If you want, well, let's start with this. If you wanted to draw a picture, we could make this arc the same as something else. And if we did that, then we would automatically know the size of this angle. Does anyone remember what we said? If this arc is exactly the same as something else in this picture, then you automatically know the size of this angle. Just like if I said to you 1 foot, you automatically know it's 12 inches. It's the same idea. So what would this arc have to be the same length as? And if it was, you would automatically know the size of that.
Arc has to be the same length as the radius.
Okay, so that's the first part. If this arc is exactly the same length as the radius, then how big is this angle automatically?
90 degrees.
Not 90. Come on. No, it's not going to be, it's not in degrees. It's not in degrees. Yeah? 1 what? Yes. Right. If you make this arc exactly the same size as the radius, then this angle is automatically 1 radian. It's just like saying if you make the length 12 inches, that's automatically 1 foot. That's just a fact that's true. So, we're going to suppose that theta 1 is 1 radian. And then, what that means is your arc in red for S1 is exactly the same length as R. So now you've got a connection there. Right here. That's going to be half of my proportion. If the angle is 1, then S1 equals R. Why? It's kind of like asking why 1 foot equals 12 inches. That's a true fact. All right, so now I have some numbers. Now I just need a proportion to plug them into. You can set this proportion up a lot of different ways, as long as you're consistent. However you set it up on the left, you have to set it up the same way on the right. All right, I'm going to start on the left with theta over S. So that's like saying, if you read it as a proportion, this theta is to S as this is to this. To keep it consistent, what would have to go on top on the right side? See?
S.
That wouldn't be consistent. We have to follow the same pattern on the left as we were going to on the right.
Theta.
Theta
1.
1. Yep. So theta 1 is to S1. This angle creates this size of an arc, as this angle creates this size of an arc. Right? And they're directly proportional. So we can set up a proportion. And now we're going to fill in what we can in that proportion. So theta and S, we're just going to leave the same. I don't have more room down, but if you do, you could just go down. So theta over S equals theta 1 is 1 over S1 is R. Okay. Now I need to solve that proportion. And once I solve it, that will be my formula for the length of an arc. So Brandon, how do I solve that proportion? help them out? How do you solve a proportion or any proportion? Usually it's two words. This. Yeah. Cross multiply. So you cross multiply. That times that equals that times that. So when we do that out, Eric, what's S times 1?
S.
S equals, and then the other diagonal is just R times theta. That's it. So that's the formula to find the length of an arc. Now, a couple things about that formula. First of all, S is the arc length, R is the radius, theta is the angle. But way back when we started, we assumed theta 1 was what? What units did we assume?
1 radian.
Radians, right? So we started this whole process off by saying we were working in radians. That means this formula has to be in radians. Okay. In that formula, there are two lengths. S is a length, R is a length, theta is an angle. So when we solve it, we got to make sure we have the proper units. It's inches, feet, whatever they give us. So there's 3 different types of questions I can ask. You're always going to have to find one variable, and I'll give you 2. Either I'll give you the R and the theta, the S and the R, or the S and the theta. I'll always give you 2, and you have to find the third one. Okay, so let's look at this one. It says, find the length of the arc. And this time I actually drew a picture for you. You don't really need the picture, but I drew it. Find the length of the arc of a circle that has a radius of 2 inches. And the angle is pi over 4. Okay. So in order to find the length of the arc, Akira, what's the first thing that I need to find the length, if I want to find the length of an arc in a circle? Well, what do we have? Well, we've got a bunch of numbers, right? We've got all these different numbers, but we don't know where they're going to go. Like if I said to you, all right, I want you to find the volume of a rectangular prism, what would you need besides the measurements of the prism itself? Sure. Anyone help her out? What do you need? Like say I just said find the volume of this book, and I told you 1 inch by 6 inches by 7 inches. Yeah, find the volume. You can't do it with just the numbers. You also need what?
Location.
Simpler than that. You need. What do you need? Like say I handed this to a 3rd grader and I said, here, find the volume of this book. And I said, it's 1 inch by 6 by 7. Tell me the volume. Well, they couldn't do it unless they had the what? They need a formula. They have to plug all those numbers into something. So we've got a bunch of numbers here, but I don't know what to plug them into unless I have a formula. So what's my formula for the length of this arc? Elias, what's my formula? What's my formula? The formula we just wrote down. I need people to kind of focus here. It's like I'm pulling teeth. Like formula. Arc length formula. S equals R theta. Yeah, is that what you were going to say? Yeah. So S equals R theta. So here's my formula. I'm going to take the numbers, I'm going to plug them in. All right. First, I'm going to write it down so I don't forget it. Okay. Now go through the formula and fill in everything you can. Read the word problem. Somebody give me one letter that I can fill in for. Yeah. R, sure. What's R? They tell me right here. Radius is 2. S, I know I'm not filling in for S because that's the question. Find the length of the arc. So we're just going to leave that as S. So the only thing I have left is theta, so I got to fill something in for that.
You use pi over 4.
Yeah, I'm going to fill in pi over 4. Now, Sam, what's the unit supposed to be on the angle?
Degrees. Or radians.
Radians. What's the unit on that angle in this problem?
Radians.
It's already radians. Perfect. So we need radians. We've got radians. We're good to go. So just fill that in. If you're not sure how to multiply something that's a fraction times something that's not, just make the other thing a fraction like that then. And now multiply straight across. Or reduce first. You're going to have to reduce at some point. Okay, so we get 2 pi over 4. And if I reduce that, Caleb, what does that reduce to? Yep, pi over 2. Now keep in mind the big picture. What did we just find? The length of the arc. So this needs a label that represents length. What label do you think I should put? Feet, inches, centimeters, millimeters. Inches, because that's what it is in this problem. It's inches. So the length of that arc, if you did that as a decimal, that's about 1.57 inches. That's it. That's how you find the length of an arc. Any questions on that? All right, let's try one little different. Little different question. Instead of asking you now for the arc length, I'm asking for the radius. Okay, so I've got a bunch of numbers. What's the first thing that I'm going to need before I can do anything? Yeah.
What the radian is?
Okay, I am going to need to know what that angle is in radians. That's something I'm going to need in a second. But there's something I need even before that. Find the volume of this book. I got to write down the formula. And the formula requires something in this problem to be fixed or changed into radians, which we'll get at that next. All right, so I'm just going to go through in order and look for these letters. Do I know S? Yeah, what's S here? 3 pi. Arc length is 3 pi. Okay, let's go to the next letter. R. Do I know that? No. That's the question. Find the radius. So I'll just leave that like that. Now, do I know theta? Okay, yeah, what is it?
Pi over 3.
Yes, it's 60 degrees, but we have to change it to radians. If you just plug in 60, no good. 60 goes into itself once, 60 goes into 180 3 times. So your angle is pi over 3. Now, I want to get r by itself, and I'm multiplying by a fraction. It's kind of like having this. If you want to get a variable by itself and you multiply by a fraction, how do you get rid of the 2 and the 3 at the same time? Yep. Exactly. You're going to multiply both sides by the reciprocal. So the reciprocal of pi over 3 is 3 over pi. 3 over pi. 3 over pi. 3's are gone. Pi's are gone. R is the only thing that's left. Pi's are gone there too. So what's my radius in this circle if the arc length is 3 pi and the angle is 60? 9 feet. 9 feet. That's it. Okay, so a little bit, I'd say a little trickier than the first one because this time you had to change the angle to radians first and then use the formula. So in this one I had you guys find R. In this one I had you guys find S. I could also give you one where you have to find theta. You just have these two numbers and you'd solve for theta. Any question on how you would do that? You just fill in the two that you have and find the one you're missing. Okay, so last thing in 6.1, which this finishes up most of what we're doing, and then the last thing in 6.2 is pretty short, is angular velocity. So angular velocity is basically when you measure the speed of something that's spinning. It's used to measure the speed of something that spins. You don't use angular velocity to describe the speed like you're driving down the highway. That wouldn't make sense. Because when you drive down the highway, you're not moving in a circle. You're usually going in a straight line. So we already have a way to measure the speed of something that moves in a straight line. So why do we need this? Why do we have to invent some other way to measure speed besides the way we already have? Well, if you don't use this, things get kind of weird when you try to measure the speed of something spinning. Okay, so let's look at this. Look at that disk. It has 3 dots on it. Okay, a black one in the center, red one, and then a black one towards the outer edge. I'm going to go and make 1 revolution. Just like that. Which dot moved the farthest out of the 3?
The outside one.
The outside one moved the farthest. So it had the biggest distance. Now, compare the time for all these dots to do their thing. As I go around in a circle, if you compare the time that it took the middle dot, the red dot, and the outer dot to all do their movement, how do all the times compare? They're the same. So what does that mean? If something traveled farther in the exact same amount of time as something else. You and your friend both leave your house at the same time, and you end up, and you both drive the same way, same exact road, and you end up farther down the road than they do. What does that mean? What does it have to be? Yeah. That dot's going faster. That dot, you all agreed, this dot traveled the farthest, and it did it in the exact same amount of time as every other dot. So if it traveled further, it must be going faster. And that's where using linear speed is weird here, because every single point on this circle is going at a different speed as you move out from the center. Now, if we describe the speed spinning, we could say all of those dots made a revolution. Maybe that took me 2 seconds. They all had a speed of 1 revolution per 2 seconds. Their revolution speed was all exactly the same. Their linear speed isn't, but their angular speed is. So it gives us a simple way to describe the speed of something spinning. So what we are going to do is we're going to measure angular speed in radians per time unit. You can measure it in anything that measures an angle. You could measure it in degrees, or you could measure it in revolutions. And the time unit isn't important. Seconds, minutes, hours. Common angular speed you've probably heard of is revolutions per minute. RPM, revolutions per minute. Okay? But in our book, we're always going to stick with radians. So if you see a problem in the book and it says find angular speed, and you're like, well, I don't know, should I use degrees, radians, revolutions? I'm telling you, use radians. Unless they tell you otherwise. The time, I don't care. Use whatever's in the problem. Minutes is in the problem, use minutes. Versus linear speed, that's the speed I told you of something moving in a straight line. And some common units for that are measured in feet per second. How many miles traveled per hour? In Europe or other countries, it's kilometers per hour. I mean, you can use any length unit that you know divided by any time unit that you know is linear speed. Okay, those are just some common ones. And the way that we're going to convert, we're going to basically do conversions in this section. We're going to do it the same way I taught you how to do radians and degrees. If you know where a unit has to go to cancel, that's the whole key. Okay, we're going to look at where the units have to go. Now, I am making the assumption that you all know basic conversions. You have to know how to convert inches to feet, minutes to hours, hours to days, seconds to minutes, days to years, feet to yards, feet to miles, things like that. I wouldn't ask you a weird conversion like how many millimeters in a foot. No, you don't have to know that. That's a weird. Right. But basic ones you would have to know. Right, so the way we're going to do it, it's called dimensional analysis. You look at your dimensions, you look at your units, and that's what helps you do it. So we're going to start with a basic one that's not even a speed. That's just time. It's not like it's days per year or days per minute. It's just 3 days. There's no speed there. All right, so we have 3 days. So what we're going to do is we're going to multiply by conversion factors. We're going to go 1 unit at a time. We're not going to skip all the way from days to minutes. We'll start with days to hours. So when you want to convert between days and hours, what's the conversion between days and hours? 24 hours in 1 day. Now, we just have to figure out, is it 24 over 1 or 1 over 24? Right now, think of it like this. You've got days in the top. You're trying to cancel out days. So, Kaya, where would days go to cancel? On the bottom. Yep. Days, and days cancels out. And make sure you write your conversion. 1 day is 24 hours. Now, if you stopped there, you'd have hours. Now, let's go to the next one. What's the next unit smaller than an hour? Yeah, minutes. So we're going to go from hours to minutes. Where would hours have to go in this fraction to cancel out? It's going to go in the bottom. Hours in the bottom, minutes in the top. Now, I need to know the conversion. What's the conversion, Jared, between hours and minutes? 60 minutes in 1 hour. Hours. Now, if you stopped there, you would have minutes. All right, and we're good. That's what they want. So now you just multiply all your fractions straight across. 3 times 24 times 60, and in the bottom, it's just 1 times 1 times 1. So 3 times 24 times 60. So 3 days is 4,320 minutes. Hey, any question on how we change days to minutes? I mean, hopefully that seemed like pretty simple, maybe too simple, but the point is I wanted you to understand the unit and the idea of canceling the units. Because now we're going to do a rate. Okay, a rate is when you have two units in the same problem, a distance unit and a time unit. The last problem just had a time unit. It was just time. Now this is rate. Distance per time. So it says you have 50 feet per second, and they want to change that to miles per hour. What does that mean? 50 feet per second. Someone explain to me, like, what? In terms of, like, how fast you're going, like, what does that really mean? 50 feet / second. Sam? Every second you move 50 feet. So that's exactly how I'm going to write it. 50 feet per 1 second. Now you could write 100 feet per 2 seconds. That's the same thing. But that's the simplest way to write it. 50 feet per second. Now, we really have two problems here. We have to change feet to miles, and we have to change seconds to hours. Doesn't matter which one you do first. So Brandon, which one you want to do first?
We'll do
Feet to miles. So we're going to change feet to miles first. Even if you don't know the conversion, you should know where feet is going to go. Is it going to go in the top, or is it going to go in the bottom? Yeah, it's going to go in the bottom because we want it to cancel out. So miles is in the top. Now I need the conversion between feet and miles. What is that conversion? Yeah.
There's 5,280 feet in 1 mile.
Yep, exactly. 5,280 feet in 1 mile. This is why a US system is kind of a pain. I mean, who comes up with that random number? 5280? I mean, why? At least in metric, everything's like a power of 10. Or 100 or 1,000, things like that. It's nice numbers. Okay, but we have this random number, 5,280 feet in 1 mile. So, feet. If you stopped at this point, you would have a speed in miles per second. We got the right distance, but we don't have the right time yet. So next, we got to get seconds to hours. So Nikara, what's my next step up from a second? That's bigger. Minutes. So would minutes go in the top or in the bottom? Yes, in the bottom. Now the conversion. Eric, how many seconds in a minute? 60. 60 seconds, 1 minute. Another conversion, done. Now you've got miles per minute. One more. Minutes to hours. Okay, where would, if we want to get minutes to hours, where's minutes going to go in the last fraction? Yep, in the top. Hours in the bottom. 60 minutes in an hour. Let's look at our last unit. Minutes. Miles in the top, hours in the bottom. Perfect. Now let's do that out and see what we get. So if you're traveling 50 feet every second, that's 50 times 60 times 60 times 60 divided by 5,280. So that's 34.1 miles per hour. Okay, so if you're going 34 miles an hour, you're moving 50 feet every second. think about it that way, it seems like it's quite a bit. That's like double the length of this room every second. And that's only 34 miles an hour. So that was linear speed to linear speed. Now let's try an angular speed to an angular speed. And then there's one more after this, and then we're going to stop there. We're going to do I'm not going to do 6.2 part 2. 6.2 part 1. I'm not going to do that today. We'll do that on Monday, and that'll probably be about 30 minutes, 25 minutes maybe. So we could probably squeeze it in, but it'll just be better if we do it Monday, then we can go nice and slow. Right. And that'll shorten the homework up tonight. All right, 200 radians per second. That means your object is spinning around 200 radians every second. And we want to convert that to revolutions per minute. Let's do the time unit first. Elias, where would seconds have to go?
On the top.
Yeah, in minutes. Bottom. Second. Minute, and Brandon, the conversion between the two.
Per second. Oh, 60 seconds a minute.
60 to 1. Now you've got a speed in radians per minute. Okay. Next step is to get radians to revolutions. You should know the number, but if you don't, we can at least put the unit in the right spot. Sam, where's radians going to go in this last fraction?
On the bottom.
Yep. Radians, revolutions. Now, I need the conversion. How many radians in one revolution?
4.
No, it's not 4. Think about how many degrees in a revolution. 360. So now just tell me what 360 is in radians.
Pi over.
Pi over 2 is 90.
Pi over.
That's even smaller
Oh.
than 90. We need bigger. Yep, I'll get that in 1 second. Yep, 2 pi. Yep. There's 2 pi. Let's try writing it in the right spot. There's 2 pi radians in one revolution. If I wanted, I could reduce 2 into 60 before I type it in on the calculator, but I'm just going to type it the way it is. So it's 200 times 60 times 1. So 200 times 60. And then divided by 1 times 2 pi. Okay, so divided by 2 pi. So that's not right. I probably need to put that 2 pi in parentheses. Yes, that's exactly what I need to do. So the top was 12,000 divided by 2 pi. But if you don't put it in parentheses, it's going to mess up. So that's a speed of 1,909.9 revolutions per minute. 1,900. What was it? 1,909?
0.9.
1,909.9. 909.9. A lot of nines. Now, this is kind of a special unit. You can write RPM if you want. A lot of people do that for revolutions per minute. Or you can write revolutions. The slash means per minute. Either way. So any question on that one? Okay, so last problem. I'm gonna let you guys copy that down, and then we'll take a look at it. All right, so last problem we're gonna look at, it had two parts. I just want to do one part because the part A we've already done that. So I'm gonna skip part A. Part A is converting revolutions per minute to radians per second. We basically just did that here. We converted radians per second to revolutions per minute. It's just converting back the other way, right? So that part's the same. The part that's different is part B. We want to convert the angular speed to a linear speed. So the idea here is, if you want to kind of imagine what's happening, imagine you had a wheel spinning at 1,850 RPMs on a machine. All of a sudden that wheel came off the machine, hit the ground, didn't lose any traction. How fast would it take off going? Another way to think about it is if you had a rope and you were spinning it, like a rock on the end of it or something, and you were spinning it at 1,850 RPMs, and your rope was 18 inches long, and all of a sudden you let the rope go. The rope and the rock would take off straight. How fast would it be going? That's instantly converting something spinning. When you let it go, it changes to linear speed. Takes off straight. That's basically what you're figuring out right here. So we're going to start with that. Anytime you want to convert from angular speed to linear speed, revolutions is like the bridge. That's how you do it. You're already in revolution, so that's good. It's spinning 1,850 revolutions every minute. Now they want seconds, so we can do the time unit quick. We'll get that out of the way. Minutes in the top, seconds in the bottom, 60 seconds in a minute. Okay, so we've got that part. Now I want to convert revolutions to feet. Okay, we're gonna have to think about that one a little bit. But let's just figure out where revolutions would go. Top or bottom? Yeah, bottom. Now, what's different about the conversion between revolutions and feet? It's not the same in every problem. Conversion between seconds and minutes, that's the same all the time. Minutes to hours, hours to days, feet to yards, feet to inches, all those conversions are static. They never change. How many feet in a revolution? Well, that depends on how big of a circle you're making. Is it a small circle or is it a big circle? How many feet in a revolution? So, for this one, that's a revolution, right? One revolution all the way around. And how big did it say that this circle was? It said it was how big? That's how many revolutions it's making. How big is the circle? 18 inches, which is 1.5 feet. They just divide that by 12. So I'm going to change it to feet because I need feet. So 1.5 feet. What's another name for a revolution of a circle? Yeah? Circumference. So imagine there's your circle. Pretend like it's a tire. And here's the ground. This tire rolls one time on the ground, and it ends up over here. And it changes shape too. So if it rolls one time, the distance that you have from here to here, that straight distance on the ground, that is your circumference. Okay. Another way to think of it is pretend like this is a piece of wire, and you cut it, and you lay it down flat. That's the distance you're looking for. So let's find the circumference of this wheel, and that will tell me how many feet are in one revolution, because a revolution is the circumference. What did we just say the radius was in feet?
1.5.
It's 1.5 feet. What's 2 times pi times 1.5? As an exact answer with pi.
9.424.
Maybe, but that's not an exact answer. That's
Oh.
rounded.
Oh.
I'm looking for an exact answer with pi.
Oh.
Yeah, just keep it simple. 3 pi. That's the circumference. 3 pi feet. Now, I know how many feet are in 1 revolution. 3 pi. So that last conversion that you just did, that's a special one. You have to figure that one out in every problem. It's different every time. It's not static. So revolutions are gone. What unit is left in the top? What unit is left in the bottom? Perfect. Feet per second. That's exactly what you want. Now you got to just multiply everything out. So we've got 1,850 times 3 pi. That's the top. And now put the bottom in parentheses, because if you have more than one thing, we saw that messes it up. But actually, we only have one thing anyway. 1 times 60 times 1. It's just 60. So divide by 60. Parentheses won't hurt anything, but you don't need them. And that gives you a speed of 290.6 feet per second. Which is pretty fast. I think if you remember, we did the problem 50 feet per second was like 34 miles an hour. Well, this is almost 6 times faster than that. This is almost 300 feet per second. So this is almost 34 times 6 miles per hour. So it's almost a couple hundred miles per hour. But I guess fast is relative, so. Okay, any question on that? Okay, so the last part, 6.2, I'm going to save that. There's a couple examples, but there's not really much in that. So we're going to do this on Monday instead. That's what we did today. So there's not much homework on 324. It's 56 to 59 and 70 to 71. 70 and 71. Okay, if you want to write down the second one, you can. That's what we'll be doing on when you come back on Monday of academics before vacation. Okay, but 324 is what I'll be looking for. I'm going to see you guys in a couple of days.